In this problem, we need to determine the maximum length of a zigzag path in a binary tree. A zigzag path is defined as starting from any node and alternating between moving to the left and right children of the current node. The length of a zigzag path is the number of edges in the path, so a single node has a length of 0. To solve this problem, we will use a depth-first search algorithm to explore all possible paths in the tree and determine the maximum length of the zigzag path. DFS is a common technique used to explore all nodes in a binary tree or graph by visiting each node and then recursively exploring all its children. First, we initialize a variable to keep track of the maximum length of the zigzag path found so far. The longest zigzag function is the starting point of the algorithm. This function calls the DFS function, which is detailed later, to start exploring the tree from the root for both the left and right directions. The DFS function calculates the maximum length of a zigzag path in the tree. It receives as parameters the root of the tree and the Boolean variable isLeft, which indicates the current direction of the zigzag path. If the tree is empty, meaning root is null, the function returns 0 because there can be no zigzag path in an empty tree. If the tree isn't empty, the function performs the exploration to the left by moving to the left child and continues the exploration with the reverse direction, right, by making a recursive call. DFS of the value in the node pointed to by node, length plus 1 and false. Simultaneously, a new path is started from the right child with DFS of the value in the node pointed to by node, 1 and true, resetting the length to 1 and changing the direction. If isLeft is false, a move to the right is made and exploration continues in the reversed left direction with a recursive call, DFS of the value in the node pointed to by node, length plus 1 and true. In parallel, a new path is started from the left child with the DFS of the value in the node pointed to by node, 1 and false, resetting the length to 1 and changing the direction. This approach explores all possible zigzag paths in the binary tree, starting from each node and alternating directions to find the maximum length of such a path. The DFS function is called from the longest zigzag function, which initiates the exploration, ensuring that all paths are considered. For instance, consider the following binary tree. A possible zigzag path could start from node 1, move to node 2, then to node 4, and finally to node 7. The path would be 1 to 2 to 4 to 7 with a length of 3. To achieve this, we use the DFS algorithm in the DFS function. We first check if the current node is null. If it is, we return 0. Otherwise, we update the maximum length of the zigzag path by comparing the current length with the maximum length found so far. If the current direction is left, we make a move to the left child and continue exploring with the right direction. Simultaneously, we start a new path from the right child. If the current direction is right, we make a move to the right child and continue exploring with the left direction. Alternatively, we start a new path from the left child. This approach ensures that all possible zigzag paths are explored, starting from each node and alternating directions to find the maximum length of such a path. The DFS function is recursively called to explore all nodes and their children, updating the maximum length as it goes. In conclusion, to solve this problem, we use the depth-first search algorithm. The longest zigzag function starts exploring from the root of the tree. If the tree is empty, meaning root is null, it returns 0. Otherwise, it initiates DFS in both directions, left and right, to explore all possible zigzag paths. The DFS function updates the maximum length of the zigzag path and recursively explores the tree, alternating directions to ensure all possible paths are considered. This method guarantees that we find the longest zigzag path in the binary tree efficiently. By using DFS, we can traverse each node once, making the solution both effective and efficient in terms of time complexity. Now, it's time to test this implementation. You can always try out your own ideas and other implementations to find other solutions to the problem.